Sir, welcome to the platform. Uh,
Thank you. I'm sorry, my camera is not working. So, but however, I think I can share my screen, so that's not a problem.
the Professor Rao is now currently working as a technical director in Akri Infotech Private Limited with 22 years experiences. I think some echoes are there.
Echo is there? Okay.
He also acted as a adjunct professor in CFD Virtual Reality Institute. His expertise in the computational fluid dynamics with over 30 years experience. He has earned his BTech in aerospace engineering from IIT Madras and has done his master's degree as well as PhD from University of Florida, US. Please share, sir, share some expertise of yours with us. Sir, please start.
Thank you. Let me share my screen. I'm sorry, my camera is not working, but I can share my screen. Are my slides visible?
Yes, sir, it is visible, sir, visible.
Okay. Okay. Good evening to all of you. And thank you, Professor Smithrupa Pradhan, for inviting me. Uh, and I'm very honored to be here. And today I hope to share with you something about how we can use machine learning in engineering and science and the sciences. I am the technical director of effectively two companies, Acri Infotech Private Limited in India and Analytic and Computational Research in USA. And let me start off with a brief outline of my talk. Why should engineers and scientists use machine learning? Uh, I think the talk itself is motivated by the fact that most machine learning is now being done by people who are just programmers, data analysts, computer science people, and so on. But I think, at least my personal opinion is, engineers and scientists can use it very effectively. And if it is to be applied in engineering and the sciences, you also bring the domain knowledge to the table. So that is the motivation behind this talk. So I'll start off with a few. I will assume that most of my audience does not know about machine learning, and I'll start off with the basics of machine learning concepts, and then I will also talk about how to work with physics-informed neural networks, which is basically a way of bringing domain knowledge, our engineering and physical domain knowledge into machine learning. And I'll talk a little about the digital twin and a little bit about point clouds and a couple of case studies followed by summary and conclusions. Um, can you confirm that my audio is okay? It's understandable?
Yes, sir, it is
Okay.
audible.
Yes, sir, it is okay. Okay, sir.
Okay. Very good. Thank you. I'm an aerospace engineer by training. My BTech is from IIT Madras. I graduated with my BTech in 1988, and I have PhD in same discipline from the University of Florida, Gainesville. And I'm basically a specialist in computational fluid dynamics since '96, and I've been a technical director of ACRI since 2002. And since 2018, we have been doing machine learning and specifically physics informed machine learning. So, okay. So, why machine learning? Okay. I think most of us know that machine learning has suddenly become very popular in the last 10, 12 years. And it already plays a very important role in our lives, like handwriting recognition, image recognition, and for more serious applications, medical imaging, video processing, speech recognition, natural language. You can talk to your computer, you can talk to the machine. And of course, one of the characteristics is it can perform very complex tasks like these, but we also know that they require lots of data to train. And basically, because it extracts relationships and rules from typically from very big data. And of course, why is it so valuable? Because it provides a way to solve very complex problems, especially when we do not know how to solve the problem or give instructions to a computer on how the problem is to be solved, or when a well defined solution methodology is not available, it helps us to proceed. Okay, coming to engineering, we have some very interesting applications, including self-driving automobiles, robotics, especially path planning, mobile robot locomotion, and how it can locate itself in space or how it can locate itself as to where it is and so on. It's also helping us to improve scientific and engineering simulations like CFD, FEM, and so on. And on general scientific research, you can do genomics, computational chemistry, computational biology, climate modeling, etc. And I'll dwell a little upon digital twin and how it can be used for things like anomaly detection, conditioning monitoring, predictive maintenance of equipment, inverse problems, etc. I may not have time to go into inverse problems, but I'll touch upon the others. In science, you can talk about, for example, it's already playing a big role in computational chemistry. In astronomy, also, things like solar flare prediction, supernova classification, getting images, classifying stars and other things from images of the night sky, things like that. Particle physics, trying to extract particle tracks and from separating it from the noise, phase transitions, bioinformatics, genome biology, and so on. So it's already being used in a lot of places in engineering and science. Now let's go into what is machine learning. you know so a simple definition is it's a field of study that gives computers the ability to learn without being explicitly programmed. So now, a more complicated and complete definition would be a computer program is said to learn from experience with respect to a given task and some performance metric if its performance improves with experience. So this was an definition by Dr. Tom Mitchell in 1997. Of course, we simplify all this. We are very practical engineers, so we say we fit models to data by minimizing the error. So that's a working definition that we have at Acri here. So I think for our purposes, that is probably the best one. Now, what are the different types of learning? You know, so one of them, the first one and the most important one probably is supervised learning. In supervised learning, the data for training and fitting a model comes with known correct answers. For example, if you have measurements of a fluid flow or the temperature field in a heat transfer problem or in a flow problem, you know the correct answer either by measurements or by CFD or finite elements or whatever. You can train a model with by applying the known correct answer and then minimizing error so that it fits the correct answer. So the error is also called a loss function in machine learning literature. It's a measure of the error in the model. And we will go into different definitions of the error shortly. Then once you have trained the model, that is the unknown coefficients of the model are fitted, then you want to see how well it will do on unseen data or data, new data that's not been used. So you can use it in a predictive mode, and the you can see how well it does on a test data or validation data. So that is the essence of supervised learning. And much of machine learning is based on supervised learning. Then you have unsupervised learning, where you don't really have the correct answer. The data does not have a correct answer attached to it. Here you use machine learning or models to find the patterns in your data. So typical usage is like clustering. You can cluster together similar items in your data, or you can use it for dimensionality reduction or compressing your data. So if it is very large, so on. There's also reinforcement learning, but I don't have the time to get into that here in this talk. Now, what are the different problem types we deal with in machine learning? First and foremost, most of you probably are already familiar with regression. You must have all fit a straight line to data, so that is one type of machine learning. So if you have higher order models like higher order polynomials or neural networks and so on, then that is the domain of machine learning. Here, the model outputs are continuous variables, like, for example, the velocity field in a fluid flow or the temperature in a heat transfer problem and so on. And these vary continuously with respect to your inputs, which are typically your geometry and boundary conditions and so on. So your loss function typically will be the mean squared error. You can also, of course, augment it with other things, but typically the mean square error is minimized by an optimization procedure. And then the coefficients of the model, your machine learning model, are fit to minimize this error. A typical metric is the R squared value, which is the coefficient, also called the coefficient of determination here. Now, the other problem type is a classification problem. Here, the model outputs are discrete values. Typically, is my email that you get spam or not spam? So that's basically either true or false. Or if you have a flow, is it turbulent or laminar? So that those are binary classification problems. There are two possible answers, true or false. You can also have a general categorical variable. For example, a multi-phase flow regime is a flow bubbly, slug, churn, and it can mean any of these different states. Each is a category by itself. So then it's a categorical, the output is a categorical variable, and we have several different mutually exclusive classes to be predicted. So here the loss function is typically binary cross entropy. I'll go into that a little later, the detail formula for that. Binary cross entropy helps you to decide whether a problem is a true or false or a 0 or 1 type problem. And categorical cross entropy is used when you have a variable that can take on several mutually exclusive values, like your multi-phase flow. Here the metrics are a lot more. You have the usual concept of accuracy, which is how many items you got right. Both true positives are those where you predicted correctly whether it is a 1, and true negatives are where you correctly predicted whether it's false answer. Similarly, false negatives are where you got wrong predictions. Something that is true was falsely predicted as false, and vice versa. False negatives and false positives. And then there are other metrics for the accuracy, like precision, recall, F1 score, and so on. And one typical issue with this is you don't have equal number of data of each category. Sometimes some of them are very less in number, some of them are many more in number, and so on. So that time you have to modify your loss function to account for the rebalancing your data. Okay. Now let's talk a little bit about the data. You have data comes in several different formats. One of them, the most common form, is structured data, where your data can be organized in a tabular form or in form of tables. So typical examples are, if your data is in Excel in a spreadsheet, or in a relational database like MySQL or Oracle database or something, which can be extracted using structured query language SQL commands, then the data is in a tabular form. You may have more than one table which are all related to each other, so that's okay. This kind of structured data is best modeled using gradient boosting decision tree, such as XGBoost or Rhino Forest. The other common format of data, and as engineers typically we will deal a lot with that, is unstructured data, which come as images, video, audio, time series, point clouds, and so on. And these are best handled by deep learning and neural networks. And the immense popularity of machine learning in the last 10, 12 years, or maybe 15 years, is mainly because of advances made by deep learning on images and video and things like that. Okay. Now, quickly take you through the basics of machine learning. This is the formula for the mean squared error. I assume that most of you have, if you have fit a straight line to some data, you're probably familiar with the mean squared error loss, which is basically the difference between the predicted value and the true or correct answer squared and then averaged over the entire data set. So this is basically used for regression problems. The cross entropy, on the other hand, you may or may not be familiar with. Here the loss is basically the negative of the log of the prediction. So the y in the second formula, the cross entropy formula, the y hat or the y, with a hat on top, yi with hat on top, is basically the probability that a prediction belongs to either true or false, typically. So you take the log of the probability times the correct answer, which is yi, which is typically 0 or 1, and summed up over the entire data set. And negative of that is the loss function. And this is what you try to minimize to get the model to fit a categorical problem. And once you have fit the model to the training data, you have to go through a process called cross-validation. Its accuracy must be evaluated on unseen data. That is, unseen data means data which has not been used to fit the model. Because for training data, you already have the right answer, right? But you want to use the model to predict unknown data points. So you have to see how it will do on the unseen data. So one of the problems in machine learning that you may encounter is called overfitting, where the training data is fit very well, very accurately, but new data, the performance is very bad or very inaccurate. So to avoid overfitting, there are a variety of techniques. Best way is, of course, to collect more data and fit it on much more data. But there are many other techniques to avoid overfitting. There are also many cross-validation techniques. One is holdout cross-validation, where you take a certain percentage of the data you have, you mix up the data very thoroughly, so there is no bias in the data. Then take 30 or 20 or 30 or 50% of it and set it aside to act as a validation data, and you train only on the remainder of the data. Stratified cross-validation is when you have many different types of items in your data which are not well balanced. Say, for example, I want to see whether a multi-phase flow is slug or churn or bubbly or whatever. And I have only 5 data points for slug flow, but bubbly flow I have 1,000. So that is unbalanced data, and so therefore we must do stratified cross validation to make sure we don't miss out any. If you divide it equally, you'll probably end up missing out some important data points. And k-fold cross validation is when you divide your data into many pieces or chunks, and then you set aside, you do holdout cross validation on each chunk of the data. That is, suppose you do tenfold cross validation, you reserve 1/10 of your data, you divide your data into 10 chunks, and then you train 10 different models, each one of which is trained on 9/10 of your data, and 1/10 is held out for validation, cross validation. So you can do that if you have less number of data items. But if you have a lot of data items, large amount of data, you can do a whole row cross validation, which is good enough. Then I'll talk a little bit about dimensional reduction later. But this is an important technique which comes under unsupervised learning. Suppose you have a data set with 1,000 or 10,000 inputs. So that is a very large data set, and it's going to strain your computer capabilities if you are fitting that much of data inputs to your model. So dimensional reduction is a technique to reduce the number of features in the data while you retain the most important ones.
The slide is not changing, sir.
Hello? Screen is not
Slide is
changing?
not changing, sir.
Oh, screen is not changing. Okay.
Yes, sir. Now it is okay, sir.
Now it's
Good,
okay?
sir.
Okay.
Okay, sir. Thank you, sir. Thank you.
Oh, okay. Okay. Which ones did you miss?
The
Did you
dimension, the cross validation.
cross validate? Oh, after cross validation, it did not change?
Before that, two slides, sir, it did not change. Now it is changing, sir.
Okay.
Loss function.
Did you see this one, or did it not change at all?
Now it changes, sir. Okay, sir. Now it is okay, sir.
Now it's okay. But did you miss this slide in the first one?
No problem, sir. No problem, sir.
Okay.
You explain, sir.
Okay. Okay. Maybe I should, go over this. Maybe I should repeat the thing on loss function, because there are some formula there.
No problem, sir. No problem, sir.
Okay. So this is the first formula is the formula for the mean squared error. It's the difference between the true value and the predicted value, and averaged over the entire square of that is averaged over the entire data set. And we try to minimize that. Most of you are already familiar with it from fitting straight lines to data. The second one probably is for, may not be that familiar with. It's for cross entropy loss. It's used for classification problems. In classification problems, suppose you have only two values, either true or false. That is yi, and your prediction is the y hat. So you take the natural log of y hat, or any log. It's not really important whether you take log 10 or log to base e. So you take the logarithm of the prediction probability, and you multiply that with the correct value, and the negative of that summed over the entire field is the loss function, and this is what you try to minimize to get the right model, the trained model. I think cross validation. Should I repeat cross validation?
No, sir. No, sir.
Okay. Dimensional reduction, you want to reduce the number of features in the data while retaining the most important ones that are critical for the accuracy of your model. A typical approach is called principal component analysis, or PCA. And interestingly, I believe it was invented in the 1940s by an Indian mathematician named Kosambi. He was a co-inventor of this technique. Okay. Okay. Now we come to neural networks. Okay. So this is what has made the machine learning so popular in the last 15 years or so. Artificial neural networks. So on the right side, can you see my picture now?
Yes, sir. Yes, sir.
Okay, good. So on the right side, you see a picture of a typical neural network where you have your inputs, which is the input layer in green color, and it's connected to several neurons in a one or more hidden layers. And then you get the output from the model, which is your yi. So your xi's are the input. It goes through hidden layers, and your output layer is the yi. And what happens here is you can see the arrows. The arrows represent certain coefficients of the model. So your input is multiplied by certain coefficients and then summed up together. And then it passes through a nonlinearity, a nonlinear function. And then that gives you the h1, h2, h3, which are numbers that come out of this process. And you can have one or more hidden layers. So each layer serves as the output for the next layer. And then finally you get the output layer, which is your correct answer. And what you do is when you're training the model, the coefficients that are represented by these arrows are adjusted by a process called automatic differentiation to minimize the difference between the output of the model and the correct answer. So if you are doing a regression problem, it will try to minimize the mean squared error, your y hats, which are the model outputs. So a typical artificial neural network has at least one hidden layer. And if you have more than a few hidden layers, it's called a deep neural network or deep learning. So there are various types of these neural network architectures. On the left-hand side, you see what is called a convolutional neural network, which is very good for processing images and maybe video. As you all know, an image consists of a grid of pixels in the x and y directions. So such kind of it's a very structured layout where the pixels are described by indices in the horizontal and vertical directions. So a convolutional neural network is very suitable for analyzing images and for classifying images and so on. If you have time series data or time varying data or data presented as a sequence, then you need some sort of a recurrent neural network. So your hidden layers are sort of connected backwards to each other so that you can go through many recurrence of the same weights. There are many variations on the recurrent neural network. The most popular one is called LSTM or long short-term memory network. So the one on the right, recurrent neural network, is very suitable for sequence data or time series data. And typically for audio classification or for analyzing speech or for analyzing a time series. Your large language models are very deep variations on a recurrent neural network. Modern variants of a recurrent neural network. Okay. Now we come to the most important part of the talk today. It's called physics-informed neural network. And this is where we come in as engineers and scientists. Okay. So this kind of thing has to be done by someone with both an engineering or scientific background and knowledge of machine learning. Because what we do here is we have a standard neural network, which you see in green on the left-hand side. So for example, suppose you are training a model on a fluid flow problem. Your inputs are typically your boundary conditions, material properties, density, viscosity, specific heat, and so on, depending on whether you're solving a flow combined flow and heat transfer problem or whatever. And you have out as outputs the velocity field, that is the three components u, v, w, and pressure. And if you have any other outputs like temperature and all that, those will go in. So that is what is represented in green. And you will train that on any measured data or CFD data or something like that. But you want your neural network to always honor the physical laws. Okay, so number one problem uh, with applying neural networks in engineering and sciences is you definitely don't have as much data as you have for regular machine learning like images or large language models and so on. For large language models, people have fed in the entire Wikipedia, entire huge amounts of data have been used in training. Similarly, if you are looking for pictures of dogs and cats and other animals, you have literally millions of images of cats and dogs on the internet, which you can take, or you can click your own pictures and train your neural network. But when it comes to engineering data, you don't have as much data. You can't, for example, do millions of experiments and collect data from that. You can't do millions of CFD calculations and collect data from that to train your neural network. So you may do a few simulations, maybe 10, 15, 20, but you can't really do much more than that, right? Because of it's very expensive. Or if you're doing experiments, then the amount of data you collect will be even less because experiments are even much more expensive than doing FEM or CFD. So what you do in such a case, you would like the outputs of your neural network, you want to regularize it in some way so that you don't do overfitting on only your training data, right? And you want the output of your neural network to honor the governing equations that are a domain knowledge that you have over the last 200 or 300 years of engineering knowledge. You want to somehow build that into your neural network. You don't want to start it from scratch. So here you have the governing equations. You can write it in residual form. Since I'm a CFD person, I've written down the governing equations of fluid flow on the in the red box on the right side. But you can use any other relevant physics or governing equations or domain knowledge for this purpose. So now what you have is you, your machine learning or physics informed machine learning has additional information by which you can train your network. And you can always, by affixing this as the last layer of your neural network, you can ensure that if your network is overfitting and performing badly on a new problem, the residuals will immediately tell you that your answer is no good and you have to go for more training, right? And you can train even on minimizing the residuals rather than only the mean squared error. So these are the advantages of doing a physics informed neural network. And the concept came about in 2018. And after that, now if you search in Google for physics informed neural networks, you have 10,000 more, tens of thousands of papers in the, that have come through in the. So basically, it's a way to make your deep learning problem learn both from data and you have embedded also the knowledge of the physics in that. I'm going to call it a spin for physics informed neural network. And I'm speaking from the viewpoint of a CFD person, but you can apply it to anything for which you already have domain knowledge in the form of equations, any sort of equations. So these are the advantages of a PIN, physics informed neural network. You have much more confidence in your results because it's not only trained on data, but also the physical constraints are honored or accommodated. It's also much more robust when evaluated outside of its training data, or rather you can minimize or reduce the level of overfitting that you do. The results can be better understood because they satisfy the governing equations. It works with less amount of data than a usual neural network, It can even work with no data because you can train only using the physics. It's much harder to train using only the physics, but it can still be done. In which case you can solve it as a mesh, you can view it as a meshless method for solving a governing equation. You just need to solve at the discrete points, arbitrary discrete points in your field, and you can get the results. You can get to train on the results. So you can combine CFD and with machine learning by using this to improve modeling effectiveness. Other advantages include you can embed novel constitutive laws, example, novel turbulence models, combustion, multiphase, and so on. You can bake in data from measurements, from DNS, from large eddy simulations. You can ensure that certain symmetries of the flow, like Galilean invariants, are preserved. You can accommodate experimental data, CFD data, all in the same set. And it's been used for generation of synthetic turbulence at inflow boundaries for LES and DNS. It's been used for modeling of turbulent combustion, including reaction rates and subgrid scale models for LES and so on. And the context of multi-phase flow, you can use it to predict bubble sizes in multi-phase bubbly flows. You can use it to compute the curvature of interface between two immiscible fluids. So in a regular CFD code, the computation of curvature and incorporation of surface tension is very computationally very expensive, and a trained artificial neural network, or actually PIN, physics informed neural network, can substantially reduce that computational effort. There are more interesting variants of pins that have come up in the last 3-4 years. One is called deep operator network. So the operator network generalizes the physics informed neural network to work across a variety of boundary conditions, initial conditions, material properties, sources, sinks, and so on. So it's basically a combination of a branch network and a trunk network. The branch network encodes the boundary conditions, initial conditions, fluid properties, sources, and so on. The trunk network brings in the effect of the coordinates x, y, z, and time, and then it takes a dot product of the two to give the final result. Now there are more improved varieties of the deep operator, physics informed deep operator network today. I didn't have the time to include a detailed explanation, but if you contact me later, I can discuss those with you. It's called neural implicit flow. So the dot product is replaced with yet another neural network. So I come back now to how you can do dimensionality reduction using neural networks, including physics-informed neural networks. This is called an autoencoder, and an autoencoder basically learns to reproduce its input, echo its input to the output via a bottleneck layer called a latent space. So the green box tells you your input. Your red box is the latent space, which is a reduced dimensionality latent space. And then the blue box on the right is the reconstruction of the input. And if we have done a good job, the mean squared error between the output reconstruction and the correct answer should be as close to zero as possible. So that means your latent space then does a very good job in representing the problem. And this has a whole bunch of different uses. One of them is to compress the initial and boundary conditions, material properties, and so on from a field, from field data. The second, another use is since the latent space is of reduced dimensionality, you can write the governing equations in terms of these new variables, and you have saved yourself a lot of. You don't have to solve as many governing equations as you did before. So instead of solving, for example, 6 governing equations, you can solve 2 of them in a transform space. So that gives you substantial reduction in the computational effort. And we'll show an application of this in the case study that we have done. Another important application that's, or rather, another application that is rapidly gaining importance is machine learning on point clouds. So on data, your data is represented on point clouds on some discrete points in space. So one way to generate point clouds is by using your 3D scanner. So by using your 3D scanner, it fires a laser at an object and it measures the time of flight and gives you your XYZ coordinates and other attributes like color and so on. So for example, you can just take a 3D scanner and take a scan of your entire building or house or whatever, and you can reconstruct a geometric model of your entire house using that. And we can bring it to fluid flow. So we can do CFD on individual points, on maybe even millions of points. So it's very flexible and saves you a lot of mesh generation time. And you can solve the partial differential equations or governing equations on the point cloud. There are various ways of solving that. One of them is the collocation method. And this method was actually invented in 1998. But at that time, the computing capabilities were not powerful enough to make use of it. So now your computers are powerful enough. You have GPUs and all that, so you can make use of it. So this is a very good way of solving ordinary and partial differential equations on point clouds. So this is a continuation of point cloud. So this is one way we are using, because point clouds are very unstructured, random collection of points, and if you have like millions of points or billions of points, sometimes scanners can give you literally billions of points. I've worked with data sets that have 30 billion points. That is 10 to the 9, 30 times 10 to the 9 points. So here we can use, you cannot even load it into typical computers because the data set is too big to be loaded into the RAM of a computer. You may have even a terabyte of RAM, it still won't do the job. So here we use special techniques called either graph neural networks or KD tree or octree kind of networks to do domain decomposition of the point cloud. And this is a very popular reference that I've cited here for that. So this is a useful way of solving point clouds, and we have used it in our own work. Are my slides changing?
Yes, sir.
Okay, good. Thank you.
Yes, sir. Yes, sir. Yes, sir.
Okay. So now we come to digital twins. This is also a topic that is, in fact, General Electric, GE was promoting it in a very big way in 2018, 2019 and all that. But I think COVID sort of put a stop to or reduced its popularity the COVID years. So what's a digital twin? Why I'm introducing digital twin here is because it's a very good use case for physics informed machine learning. So a digital twin is a digital representation of any physical asset or any process. So for example, let's say your aircraft or your automobile, you can have a digital twin that represents it both geometrically as well as the um, strength of the materials, how many fatigue cycles it has gone through, and things like that. So it's an up to date and real time representation of your asset. So that also means it is getting real time data from your asset through IoT and sensor networks and so on. And it's data driven typically data driven model, which of course can be enhanced with physics based or physics informed machine learning. Um, so it's a comprehensive model of your system, and it's updated even during the operational phase. So that tells you the actual state of your system. For example, a few days ago, my car in which I was traveling broke down because its coolant leaked out very suddenly, and the engine block seized up. So I was stuck in Delhi for 2 days because of that. A digital twin would have really given early warning of such a problem, and prevented the engine from getting destroyed. So that is the kind of use to which a digital twin can be put. So this is a pictorial representation of a digital twin. So in the center, you see the logical digital twin, a block diagram. And on top, you see the Internet of Things, IoT or sensor devices, and so on. So the IoT device will typically be like a PLC, programmable logic controller, that will be connected to the cloud, and it picks up data from sensors, and maybe even maintains a database of the entire history of what happened to the product. And you can use a physics informed neural network to model as many components of the system as is feasible. This is another, so you have your equipment. A digital twin is basically your physical hardware plus your machine learning model, typically, hopefully physically, physics informed, plus your IoT devices which have sensors and on the hardware and then communicate. And can actually, these PLCs can run the neural network in a predictive mode to tell you if something is wrong or what is the remaining useful life and so on. So what is the use of a digital twin? You can use it for predictive maintenance. So instead of replacing parts on a fixed schedule, you can replace the parts only if they are actually getting worn out or damaged. You can also do remaining life estimation of parts, and you can build models of your system, good models of your system for making controllers which are more robust and stable. And all of the above, even if your asset is not easily accessible. For example, if you have offshore structures such as drilling platforms and so on in the middle of the sea, you can use digital twins to know the state of that asset, or control that asset without actually taking a ship to go there. So it enables real-time monitoring of the physical asset, predictive maintenance, better control and performance optimization. And nowadays systems are so complex, so you need better ways of dealing with them. So digital twins can have the potential to give you safer and better products, basically. So why the great interest in digital twin in the last 5-6 years? Because of several enabling technologies. First of all, we have much better and more powerful small computers and IoT devices, industrial Internet of Things, which enable fast and cheap communication. Low-cost sensors have really dropped in cost and are much more, powerful. Machine learning has improved, so you can have accurate and efficient models of your system behavior. And people have started collecting a lot of data. You have big data for developing accurate models, keeping track of the history of the product, and so on. And you have both powerful computing resources on the cloud as well as on the edge. Edge computing meaning typically refers to Industry 4.0, 4.0, or IoT, Industrial Internet of Things. Okay. So what are the potential application areas of digital twins? Aerospace is typically where it all starts, and this is where it all started. So the very first digital twin was used in NASA's Apollo program, where a mock-up on the ground was used to guide the astronauts of Apollo 13 safely back to Earth. Apollo 13, I think, was the one where the oxygen tank exploded, and they had to come back to Earth. So a mock-up, a physical mock-up, or a digital twin, because they duplicated all the computers on the craft inside that digital twin. And manufacturing, again, Greaves in 2002 came up with a digital twin, or the virtual factory concept, where all the manufacturing processes are replicated in a digital twin. Then digital twins are there for buildings. We ourselves have done some work using point clouds, building digital twins for buildings after they are scanned with the point cloud. So one of the uses for buildings is to know the as-is dimensions or as-is condition of the building. Then other uses can be for ventilation, plumbing, wiring, thermal models, and so on and so forth. Automotive, Tesla has a digital twin for every car it makes. And ANSYS has done some prototype digital twin for braking system of automobiles. And other places where you can use it are ship design, process optimization. Healthcare is again a very big area. Remote surgery, robotic surgery, and there are ambitions for making digital twin for the full human body, so that they can do personalized medicine. Singapore has made digital twins for its entire power grid, so you can have digital twins at either small scales, large scales, for various purposes. So how do you create a digital twin? It's one of the main consumers of physics-informed neural networks. So it consists of machine learning models. Of course, it consists of the geometry. You have to have accurate geometry in the first place. Then physics-informed neural networks, and then trained using both simulation data, CFD, FEM, multibody dynamics, electromagnetic computations, multiphysics, and etc., plus data from measurements. So you can combine the two to get things. And then you can continuously update the digital twin in real time from IoT and sensors. So you can burn it into your IoT hardware, or you can burn it into your ROM of your computer. Use of edge computing for fast evaluation of machine learning models. To integrate it with both IoT sensors as well as the cloud. So you can, in the cloud, you can do background processing of your data to get the latest update of your assets. And the IoT helps to do part of the processing is done on edge or a PLC or whatever. And the sensor data is, of course, assimilated in real time. So digital twins, of course, will be periodically updated to include new simulation experimental data and to extend the range of your operating conditions. So how will you, as engineers, how will we apply a digital twin to our products that we design and develop? We can generate high fidelity CFD FEM simulations for any component. These become training data. You can train your deep neural networks and machine learning models on that. Embed the model in a digital twin, integrate data from sensors via IoT, update the digital twin, and repeat for the life of the product. So you will have a digital twin which is updated continuously as part of the product life cycle. How am I doing for time? How much time do I have left?
Okay, time.
Hello.
Hello, yeah.
Yeah. Sir, it will be continue up to 9 o'clock
Okay.
actually, but if you then you will finish by 8:45, then some open discussion for the question answer round, then
Sure,
we will conclude.
sure. Okay, then I'll speed up a little bit. So this is a case study that we did. Um, yeah, this was for an automobile cooling system, and the our client wanted to simulate the process of filling the system with a coolant. So you have the typical coolant system with a pump, with a radiator, with a lot of tubes, a reservoir, and so on. And what happens is when it is being filled with coolant, sometimes you have air bubbles stuck in different places of the system, and this causes a performance loss during operations. You know, so they were doing CFD studies of coolant filling, which is basically a multi-phase volume of fluid approach with sliding measures and multiple rotating frame of reference for the pump. And a typical simulation was taking a long time uh, on on um, on a cluster of computers. It was taking a couple of months. So that was too slow, and that was a showstopper for them. So they wanted to see whether they could speed it up by some mechanism. So they approached me. So we came up with the idea of replacing some of the components with machine learning models and then embedding it into CFD. So basically, what we did was we constructed a machine learning model or a digital model for the channels of the radiator, and we could train the model by just looking at the CFD of flow inside a single pipe. And because it has hundreds of pipes, we removed the entire CFD mesh of the radiator with a neural network. So once you do that, uh, you know, you get a substantial reduction in the mesh size, and once you get a substantial reduction in the mesh size, uh, it 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 basically just removing the radiator from the CFD and replacing it with a machine learning model gave me a 25% speed up. Okay. And then we started replacing the other components like the battery pack, the pump itself, with other machine learning models to get a substantial performance improvement over the thing. So wherever you have a repeating component, we could replace it with a machine learning model. And we took the machine learning model and connected it with the CFD code to get the actual speed up. So for the full system simulation, we got 25% by replacing only the radiator tubes with the artificial neural network. So we embedded that into the CFD computation itself, and the CFD computation was, speeded up by about 25% just by removing the radiator tubes. So each time you replace, for example, the pump, the battery pack, and so on, you get further speed up of that. So this was a very interesting coupling between CFD and machine learning. Um, and another computation that we did was for steady flow in porous media. So this is basically a simulation of groundwater flow. For groundwater flow, we were interested in steady flow in 3D, saturated flow inside the soil. You know, so we had a fixed head boundary conditions at the lateral boundaries, and so basically you have groundwater. This is basically soil, and you can see the top is having some kind of topography. The ground is not flat, you have some hills and valleys and so on. And of course, the flow, the pressure is atmospheric pressure at the top of the soil, and you have zero flux boundary conditions at the top, which basically means there is no rainfall. If you have rainfall and the water is leaching into the ground, then you have some kind of flux at the top. And we wanted to basically see how well we can simulate this with machine learning. So first we generate, so pore flow is a CFD solver which is specialized for groundwater flow. So it simulates the Darcy flow in heterogeneous porous media like soils and rocks and so on. And so this CFD simulation, so about 2000 CFD simulations were performed, and uh, the 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 domain extent was basically something like uh, about 2 to 3 kilometers in each direction. So the CFD simulation include variations in the geometry and topography of the soil. So we had different soil layers at different depths. Typically, we did the simulations with up to 11 layers, with the hydraulic conductivity varying very substantially from 10 to the minus 9 meters per day to 10 to the minus 4 meters per day. And boundary conditions were basically fixed water pressure or fixed head on the lateral boundaries, and varying from 0 to 10 meters head, 10 meters of water basically. So the domain extents went from 500 to 2000 meters basically. And we also rotate the domain so that we get Galilean invariance of the flow. And the top of domain is deformed with a lot of hills and valleys and so on and so forth. So you can see some typical hydraulic conductivity contours. So we have different soil layers with different hydraulic conductivity contours. So we want the model to learn to predict for almost any kind of hydraulic conductivity. And so about 50% of the data was reserved for training, and the other 50% was reserved for testing. It was never used for fitting the model. And so the model architecture, so I used the autoencoder, which we talked about a little earlier today, to do the dimensional reduction. Because if you throw in the full input, you will run out of memory on your computer. I mean, even a cluster of computers cannot take that. So I used an autoencoder to do the dimensional reduction. A total of 7 autoencoders were used, 1 for the field and 6 for each of the boundaries on the, 2 x-axis boundaries, 2 y-axis boundaries, and 2 z-axis boundaries. Then the latent space from all the 7 autoencoders were combined to give the boundary and hydraulic conductivity properties. So this is basically the network architecture. So you can see we have 7 autoencoders, each with many layers, and the latent space from each one is taken out and fitted into multiple. So it's a very deep network and took several days, actually more than a month to train. And then the output is then again distributed back to the field points. So basically we take the latent space from each autoencoder, pass it through some more dense layers of the neural networks, and then the output is then obtained at each and every grid point in the domain. And this was trained with about 1000 CFD cases, and a further 1000 CFD cases were used for the testing of the procedure. So there's a physics-informed operator network in the latent space. So that provides a compact representation or dimensional reduction of the boundary conditions, the material properties, force and sink terms in the governing equation. And the last layer you can see is the governing equations that are embedded into the last layer. And how do the results look? So you can see the pressure contours. So the error is about a 1% difference between the machine learning predictions and the original CFD. So the prediction includes the hydraulic head of the water and the velocity components of the water. So this is a typical distribution of the error, the histograms of the errors. So you can see it's not quite a Gaussian distribution in most cases. Some of them are quite skewed, at different locations. Okay, so I'll quickly call a conclusion, then we can go for some discussion. So I have talked about why engineers and scientists should use machine learning in their day-to-day work. I've touched upon the basics of machine learning concepts. And then our preferred approach is the physics-informed neural networks and their variants such as the physics-informed deep operator network, the physics-informed neural implicit flow, and so on. I touched a little upon digital twin, the point clouds, and talked about two case studies, one related to coolant feeling of an automobile cooling circuit, and one on steady saturated flow in porous media. And one was for speeding up the CFDs. The second one was to look at the accuracy of machine learning versus CFD. Now, I'll just say a few words about the company I work for. It's called Analytic and Computational Research. Its main company is in US, established in 1979. So long experience in CFD. Acri Infotech is in India. It's a branch of that, established in 2000. So we are basically specialists in CFD with different software products. Answer, which is a general purpose Navier-Stokes solver with heat transfer, mass transfer, combustion, reacting flow, and so on. Pore flow, which is the thing that we used, software that we use for the groundwater flow problem, which looks at Darcy flow along with heat transfer, mass transfer, chemical reactions, multi-phase flows in porous media. And tidal solves the shallow water equations along with heat mass transfer and reacting flow. And since 2018, we have been acting in machine learning. We have been active in machine learning and physics-informed machine learning specifically. And please feel free to contact us at techsupport@accuracyfd.com if you need any further assistance in these areas. And that brings me to the conclusion of the talk, and we can go ahead for the question and answer session. Thank you.
Hello.
Yes.
Thank you, sir. Thank you so much. We are honored as you are with us. On the behalf of the organizing team, I am very much thankful to you as you keep my request and deliver your talk. Thank you so much, sir.
Oh, thank you. My
Sir,
pleasure.
sir, now it is, I request all the participants to, if you have some doubt or any query, please ask, sir. It is for the open discussion. Please, if any candidates and if any participants have any doubt, please ask to the sir. I think nobody has any queries. Thank you so
Okay.
much, sir.
Thank you. Thank you.
Thank you.